Hi everyone, welcome to the first part of a three-part video series where we completely dive into the transformers. In this video, we will get an overall idea about what the transformers are and how they work. In the second video, we will go through the paper Attention is All You Need and understand the rationale behind what the authors were thinking and how they built out transformers. And in the third one, we will code everything out using PyTorch. So subscribe if you still haven't to stay tuned when the new videos come out. Let us begin with the video and get it started. Yeah. So the structure of this video is going to be, first I give you an overall idea about the transformers and how each component work and how they relate to each other. And as we move forward, we will be diving deep into each component and trying to understand how they work. So let's get an overall idea about what the transformers are and why they were made. So back in 2017, when transformers were first released in the paper Attention is All You Need, the big problem was machine translation, i.e., language translation. So translating from one language to another. So I have this super special transformer with me to which I give a sentence in English. So this is English. Let me just type that English. Yes. And I want to translate this into the language that I desire, that is Hindi. So I know what the final output is going to look like and I know what my input is. So the input is I like pizza and the output would be mujhe pizza pasand hai. So let's see how the transformers deal with this. So inside this black box that we have the transformer, the super special transformer, we have an encoder block and a decoder block. Well, actually, there are multiple encoder and decoder blocks, but we'll go into that later in the video. So meanwhile, let's assume there are a single encoder block and a single decoder block. So what the encoder block does is it takes your input in whatever language you have and translates that into an intermediate language that the machine understands. You can think of it like this: a machine does not understand English, French, German, or any other language in fact. So it converts that into an intermediate language that the machine is able to understand. So we can call it something like the ZLang. So the encoder converts it into ZLang, and then the decoder translates it back to the language that we want. So in this case, which happens to be Hindi. But before going to the encoder, this sentence must be converted into something that the machine is able to understand. So now we take this and we convert them into embeddings. So you take one sentence, break it down into words, and each word is converted into embeddings. Let's understand why we need embeddings and what they actually are. So, as I mentioned, machines do not understand languages like we do. So, how do we fix this? The what do machines understand? We know machines understand numbers, right? So it's basically bits and flip flops, so ones and zeros. So what we can do is convert these words into numbers. One way of doing that is mapping the words to specific numbers. So we can have a huge vocabulary, and for each word, we can have a number mapped to it. So for king, I can have one. For queen, I can have two. For apple, I can have three. For oranges, I can have four, and so on and on. This process is called tokenization. Now, in actual transformers, this is not the tokenization process that is used. So, this is something like word tokenization, where I am tokenizing each word. But in practice, we use something called byte pair encoding. You can read more about that by looking it up. And there are many more different kinds of tokenization methods like word to vec, globe, and so many more. So I'm just using this for brevity's sake and for simplicity's sake. So words, we understand words and how we can relate them with numbers. Now I have tokenized the words, but there's another issue. How do you define the relations between different words? So when you hear the word king, you automatically think of king, castles, royalty, queens, maybe even TV shows, right? So how do I give this knowledge, this information of how different words relate to each other to a machine? That is where the embedding model comes in. So over here, I've created an embedding matrix of two dimensions. So over here, it's x-axis, y-axis, so two dimensions. And as you can see, I've plotted king over here and queen over here because king is more closely related to queen than apples and oranges. And as you can see, apples and oranges are closer together. So more modern embedding matrices have a lot of dimensions, like the one used in the transformers had 512 dimensions, and they are able to capture the semantic meaning and relation between words and ideas way better than this two-dimensional embedding matrix. So I hope now you have a better understanding of what embeddings are. So you take a word, you take a sentence, you tokenize it, then you embed it. So you have a semantic relation of the entire sentence, or how different words relate to each other, in something that the machine is able to understand. Going back to our transformers, so we take our sentence, I like pizza, break it down into its own respective tokens, embed those tokens into an embedding. So x1 embedding, x2 embedding, and x3 embedding for each of these words, and add positional information to it. Now, the requirement for positional information is a transformer takes your entire sentence, paragraph, page, document all in parallel. So it takes your entire page. Let's say if you are working with pages, entire page tokenizes each word and then embeds it and gives it to the LLM or transformers in our case. Now the big issue that we'll obviously face is there is no intrinsic meaning of relation between words. So, how are different words related to each other? That is where we need positional encoding. Previously, we never faced this problem in LSTMs, RNNs, GRUs because the data was put in sequentially. So, the model had an intrinsic information about how different words relate to each other. But that's not the case with transformers. So, if we do not give positional information, we can have sentences like I like to uh, eat, eat pizza, and we can have sentences like pizza like to eat I, and the model will think both of them are the same sentence, and obviously we don't want that, right? So we need to give in the positional information of the entire sentence, paragraph, or page. We will dive more into how positional encoding is calculated and how it's put into the embedding vectors. So you can think of them as vectors because they are one dimensional, and so it's 1D array. So 1D array of multiple embedding values. So for each vector, we put the positional encoding to it. So the model understands the difference between how different words are related to each other. Now we have our input, we tokenize it, we embed it, we give it the positional encoding, and then we give it to the encoder block. So an encoder block has two main parts. It has a self-attention layer, and this was the one of the big revolutions of attention is all you need, self-attention, and feed-forward network layer. So let's have a general idea about what the self-attention layer is and what the feed-forward network, neural network is. So you can think of each of our tokens or embedded vectors. Let's call them vectors from now on to keep the words, like the length of the sentence, is small. I don't want to repeat myself and take a lot of time. So we take our tokens and we give it to our self-attention layer. So our vectors are given to the self-attention layer, and what it enables them to do is think. So they can look at the different tokens and different vectors and see what is their characteristics. So the boy can look at the gentleman and think about it. Okay, so the gentleman has a mustache. He can look at the lady and see, okay, she has a notepad, so she probably is a journalist or a student or something. So the boy can look at the granny and see, okay, so she's old, she maybe needs a seat to sit on, and so on. And each of these tokens can look at each other. So the boy can look at gentleman, the boy can look at the lady, the boy can look at the granny and think about them. So find relations or try to understand them on his own. And the gentleman can subsequently look at the boy, the lady, the granny, and so on and on. But they are not able to communicate with each other. They can just understand how each of them work and try to come up like have meaning of why they are here, what they can do, and so on. And that is where the feed forward neural network comes in. The feed forward neural network lets them communicate between each other. This lets them pass information, valuable information that helps us get the answer that we want. So this is how you can get a general idea about how the self attention and the feed forward network works. So now moving forward, you have the encoder. The encoder takes the vectors, gives it to the self-attention layer. The self-attention layer figures out, okay, how are different vectors related to me? How am I related to them? And then it gives it to the feed-forward network. Now they are able to communicate to each other, and they have a complete understanding between each other. Now I want to see this information translated to a language that I understand, because I do not understand the machine language. I do not understand what the machines are talking about, right? So all the output is given to the decoder, and the decoder translates it into a language that I, a human, understands and am able to make sense of. And that is more or less everything that a transformers are about. Now let's dive deep into each component of it and try to understand what is going on. Hi. So going back to the transformers diagram, let's try to understand what is going on. So we already had a look at input embeddings, and you more or less understand how they work. So we have our inputs, our sentence, paragraph, or page. We tokenize it, and we then send these tokens to an embeddings model to convert them into the input embeddings. Now let's have a look at the positional encoding and how it is calculated. If we have a look at the original Transformers paper and the way they calculated the positional encoding, they did it using this formula. Yikes! This looks a bit cumbersome and complex, right? So we'll try to simplify this, make sense out of it, and understand how it works. So POS is basically the position that we want to calculate. So position of the word. So for I, that would be 0. Like, it would be 1 because we are using 0 based indexing. I is a bit complex, so we'll talk about that in a while. 10,000 is a value calculated experimentally. It's a constant, so we can just call it n. And d model is the dimension of the embedding model that you're using. So if we simplify this and use something like d equal to 4 and n equal to 100, so over here this d is equal to 4 and n is equal to 100, and using that, if we try to calculate the positional encoding, it will make more sense. So for I equal to 0, we put in 0, and this comes out as sine 0. So that is equal to 0, and that is for I equal to 1. So as I mentioned, I wrote over here d is equal to 4, and we alternate between sine and cos. So the way I is calculated is, first we do I0 for sine, then I0 for cos. Then we do I equal to 1 for sine and I equal to 1 for cos. So we keep on alternating. And you can think of I goes up to d divided by 2. So it's written as 2i, right? So 2i plus 1 and 2i. So the way I like to think about it is I is equal to d by 2, and we alternate between sine and cos. So for cos 0 equal to 1, sine 0 equal to 0. And for I equal to 1, that is, so this is d1, d2, d3, d4. So for the third position, we have sine 0, because this is position 0, so all of these values would be 0. Now for like, that is 1, position 1, we put in the values and we calculate, and this starts to make more sense. Now let's expand this, okay? Instead of d4, what if we so sorry, instead of expanding it, let's visualize this. Yes, that's what I meant to say. So when we calculate the sine and cos values, so this is sine, cos, sine, cos. So this, you can think of this as for I equal to 0, I equal to 0, I equal to 1, I equal to 1, and you input these values, and then based on the positions, so these dots are different positions. You can calculate the value that you need. So you plot the sine wave by inputting I and dimensions. So you know dimension is fixed for embeddings models. For transformers, that would be 512. This value is fixed, and we can go I up to d by 2, and all of this is fixed. So the only variable left is the position of the word. So for different words, so 0th position, for dimension 4, I know, okay, these are the values: 0, 0.841, 0.909, 0.14. Oh, sorry, position is over here, sorry. So 0.000, 1.000, 0.000, 1.000, exactly what we calculated. So that is how positional encodings are calculated, and this is a great visualization for that. And at the first time when I looked at it, it looked extremely confusing to me. So let me help you understand more about it. So over here you can see there are 512 dimensions, right? And you can think of it, we expanding our sine and cos up to 512 dimensions, and for each dimension and each position, we are calculating the different sine and cos values. So you can see that these are alternating, right? So it's um, yellow, then green, then yellow, then green. That is because we are alternating between sine and cos, and we are calculating these values up to 512 dimensions for over here around 100 words. Okay, so 100 positions. You can obviously expand this, and that is your context length. That is all you needed to understand about positional encoding, and we can move forward now. So, moving forward, okay, where were we? Yes. Now we will have a look at the multi-head attention layer. This is one of the most complex parts about the transformers, and understanding this takes time. So, let's move forward to that. So, hopefully, you remember our embedding matrices, and let's simplify our sentence with just two words, okay? Delicious pizza. So we take delicious pizza and convert them into embedding vectors. So in practice, we actually use matrices, but for understanding sake, I am using vectors, and we will go into matrices when you completely understand how this works with vectors, then we can move forward with matrices. So you have the delicious embedding vector, the pizza embedding vector, and you then multiply it with a query matrix, key matrix, and value matrix to get query vectors, key vectors, and value vectors. So let's just pause for a moment, and I want to help you understand what these matrices are. Okay, so the first time I heard about query key values, it seemed extremely confusing to me. So why QKV? Why not any other words? Like, why not call them ABC or something, right? Or do they hold some special meaning? The truth is, they don't hold any special meaning. That's just convention, and they are called like that. These are just matrices. They are nothing else. They are just matrices. So you can call them, you can change the order even. You can call them KQV, you can call them ABC, you can call them XYZ or something. And they will remain matrices. This is just a naming convention. So you don't need to worry about understanding why is it called query, why is this called key, why is this called value. These are just matrices and nothing else. So when the model is initialized, these are also initialized. So these are the parameters that we train to get the correct query matrices, key matrices, and value matrices, and that is what we are training when we train a transformers. This gives us correct query vectors, key vectors, and value vectors, which in fact in take gives us the correct answers. So, if you want to have a quick understanding of how that works, I can go over to my blog, in which I wrote down how QKV work. Okay, so one of the biggest mysteries that I had was that when you calculate the QKV, you begin with the embedding vectors or embedding matrices and calculate QKVs using them. So how can I relate information out of a sentence that I already have, right? Now, if we go back where I mentioned to you that you can think of self attention layer as multiple vectors being present and trying to understand how different vectors are related to them. And that is what a self attention layer does. It calculates the different relation of different vectors amongst each other. So let's say I have question, I have a sentence called Pramod loves pizza. I give it to a self attention layer and then it breaks it down into Pramod loves pizza. And now loves try to understand, okay, what's my relation with Pramod? What's my relationship with pizza? So I understand as love that, okay, pizza is the thing that I love, but who am I loved by? So Pramod is the person who loves pizza. So just using the sentence itself, I can answer the question. So that is what basically the attention layer is doing. And now let's calculate it by going through the formula. Going back to the paper, if you have a look at the self attention, yes. So scale dot product attention. That is the attention equation. QKV is equal to softmax of QK transpose divided by dimension of key um, vector in our case, or in reality it would be matrix, square root of that multiplied by V. So one thing you need to keep in mind is whenever you see Q as capital, that means a matrix, and whenever you see Q in small, that means, sorry for that, a vector. So if we go back and if we use that, so you first need to calculate the QKV vectors. So QKV vectors, those are calculated by taking our embeddings, multiplying them by a QKV matrix. And the way matrix multiplication works very quickly is I take this row multiplied by this column. I take to get this value. Then I take this row multiplied by the second column to get the second value. Then I take this row again multiplied by the third column to get this value. So that is how matrix multiplications work in a very quick manner. Now I have the embedding, the original embedding, Q, K, V vectors. So first I need to calculate the score. So this is called the score, and I apologize. So this should be transpose. So Q1 multiplied by K1, and that gives me a score of 92. This is just an arbitrary value and not an actual value. It can be anything. So Q1 multiplied by K1. I also need to multiply it by K2. So each query is multiplied by all the keys present for the entire sentence. So if it was delicious pizza from Havana, right? So it would be Q1 multiplied by K1, Q1 multiplied by K2, Q1 multiplied by K3, and Q1 multiplied by K4. And now we divide that by the square root of dimension of key vector, and that gives us these values. This is done to stabilize training. That is an important thing in machine learning. Whenever you see something being divided by something and you try to understand why that is being done, one of the main reasons usually is to stabilize training. So now we have done this. So we have this whole equation. We take the softmax of that. So softmax is a very interesting equation. It looks something like this. So let me write it. So E, oh my god, that's huge. Okay, okay. So E is the Euler constant. E x, or that, wait, it would be better if I write it as I. So E I divided by summation of E um, uh, j, where j goes from 1 to n. Okay, so softmax is used to calculate the probability of any one of this occurring. Okay, it's a very interesting formula. You can put in different values and try to figure out how it works, or you can look it up and try to understand how it works. But yeah, this is how softmax equation looks like. Let me remove this. Yes. Oh no, I don't want to do that. Okay, never mind. It's staying with us. Um, Okay, so we calculate the softmax and then we multiply that by the V vector. So this softmax is multiplied by V1, this softmax is multiplied by V2. So now if you have a look, you can see this is a darker color and this is a lighter color. So it basically is telling me that for this embedding, this value has more information than this. So this is more correlated than this. So you can think of the cat jumped over the lazy dog, right? And I for the word cat, words like jump and dog have more value than the word the, because the is not adding a lot of information to the entire sentence. But dog, jump, cat, these are the main words or the nouns and verbs of the entire sentence. And that is basically what softmax multiplied by values does. Now we take these v1 vectors. So if there were multiple tokens, it would be v1, v2, v3, and so on, and sum them up to get a z1 vector. And this is our attention value. So this single vector has all my attention information for this one word. For delicious, this is all the attention value I need. Now I need to calculate it for pizza, and that would be x2. So what will I do? I'll do q2 multiplied by k1 multiplied by k2, and if there are more keys, it would be multiplied by more keys, then divide by the under root of dk, softmax multiplied by values, sum it up. So that is how basically self-attention is calculated for vectors. Now let's do that for matrices. So what we do is concatenate that. So this is delicious. So x1, what we're representing it as x1 earlier, and this is x2, pizza. So delicious pizza. We concatenate that, multiply that by the WQ matrix, and we get the Q matrix, not the Q vector. So the Q matrix, K matrix, and V matrix. And if we follow the same steps, we have our attention score Z. So Q multiplied by K transpose divided by square root of dk, softmax of that multiplied by V, and we get Z value. So this was just one attention head. So each encoder layer has multiple attention heads. And in the original Transformers paper, they had 8 attention heads for each encoder layer. So each one gives us different z values, so z1, z2 up to z8. But in the end, we want a single z attention score. So what happens is we concatenate all of these z scores and multiply that by wo matrix. This is trained along with the model, which gives us the final z. This z captures information from all the attention heads. To get a quick summary of what is going on, let's have a look at this. So we begin with a sentence, we embed it, and then we multiply that by the different matrices. So QKV matrices, which gives us the weights of QKV matrices, which gives us the final QKV matrices, using which we put it through the formula to get the Z1, Z2, and the different attention score for each attention head, which we concatenate together and multiply by the W0 matrix to finally get the Z attention score. Now, a thing that I had a lot of time problem understanding was, why do we have so many attention heads, right? Why can't we just have one single attention head, or like two attention heads? Why do we need so many attention heads? You can think of it like each attention head is represents this room. So we can think of each room as one attention head, and each attention head is a different orientation of the room. So in this orientation, the boy is seated closely to the gentleman, so he is able to understand more about the gentleman than he is able to understand about the granny. But you can think in another attention head, the granny is seated closer to the boy, so now the boy understands better about the granny than he understands about the gentleman. And this can be represented as different representations. So if I put it in a graph, you can think that the market, so this can be our original room, and this could be a different attention head. So in this attention head, the apple is closer to the market. So if someone asks me a question like, which company makes good cell phones, I can see, okay, this company Apple is closer to this cell phone, so the answer probably is Apple. But if I take representation 1, I would be confused. Okay, so do I need to go to the market to get a generic cell phone, or is the Apple company good? So it causes confusion, right? So we have different attention head, which captures different meanings, different representations of how different tokens relate to each other, which helps us answer different kinds of questions. Now let's move forward and make our understanding a bit more complex by diving deep into the encoder and decoder blocks themselves. So as I mentioned initially, we do not actually have a single encoder block. We actually have multiple encoder blocks. Like in the original Transformers paper, attention is all you need. We had six encoder layers and six encoder blocks and six decoder blocks. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So you have the sentence, you embed it, you give it to encoder 1, which gives it to encoder 2, which gives it to encoder 3, so on till it reaches the last encoder. Now, one confusing bit might be, why is it connected to each and every decoder? Why not just the first one or just the last one, right? We will dive more into that in a while. So let's understand a bit more about the encoder block and how that works, and we can move forward to the decoder block after that. So this is how encoder block overall looks like. We have understood everything there is to understand till this part. That is, we take our embedding vectors, add positional encoding to them, calculate the self-attention score for the different vectors. Z1, we have the final Z score, and then we add and normalize. So what is add and normalize? Now if we go back to our, yes, where we started with, so you see over here the way this arrow is connected. So this is called a residual network, and what that does is it puts the original information back into the model along with the calculated information. And the reason it is done is, as a model gets deeper, so a deep neural network gets deeper, you lose a lot of information that we started with, and this basically stops that from happening. So it preserves a lot of information that we might have lost if we made a very deep network, and that is where this residual network adds the original embedding vectors to this. And what is normalization? Let's try to understand that now. So our embedding vectors and all these understanding, right, they can be anywhere. So if I try to represent them in a graph, the original features, the original vectors or calculated vectors can be present anywhere. So they can be in the end of x-axis, or there was some place in the y-axis, like over here as a cluster, and so and so. But this is not desirable because this destabilizes our training, and normalizing this basically centers them. And the one term is we call making the mean zero and making the standard variance one, and that is what is happening. So we try to center all our information around the center, and this stabilizes training and helps us converge to minima faster, and that is why we normalize them as well. One important distinction though is we do a layer normalization. So if you come from a computer vision background, they usually do a batch normalization, but over here a layer normalization is done. This is a very interesting concept that I implore you to explore on your own to understand more about, because this is outside the purview of this video, but it's very interesting to understand the difference between layer normalization, batch normalization, and there are different kind of normalization as well, right? So what if I try to normalize on the sentence length? What happens then? So explore it. I will add some sources in the description box below so you can have a look at them too. Now, if you go back to the encoder block, yes. So we add and normalize. So why is that done? To preserve our information that we originally started with, so we do not lose any important things. And we again have our Z scores, and we give that to the feed forward neural network. I hope you remember what the feed forward neural network does. It basically lets the different tokens communicate between each other. So now they understand, hey, do you know about, so the boy can possibly ask the gentleman, hey, do you know what are some good watches that I can buy for my father? The lady can ask the granny about, I don't know, hair care routine or something. So That's how the feed forward neural network works, and that is what it does. It's like our traditional feed forward neural network, so no need to worry about the different architecture behind it. There's nothing complex in understanding this. It's just our traditional neural network. So the way you must have seen this, it's very popular. So this is an example of binary classifier ANN. So that is basically what the neural network looks like. And yes, I apologize for my bad handwriting. I can't do anything about it. So this is basically a feed forward neural network. This is how it looks like. So you flatten this information, pass it to a feed forward network, and that gives you your outputs. And these are our outputs. Yes, right? So moving forward, now we understand normalization, we understand encoder, and let's try to understand the decoder block. How do we actually get the information that I can understand as a human? So you start with your inputs, embed them, add the positional information, give it to the encoder. Encoder does all its magic, and now you have different vectors. So in essence, they would be matrices, obviously, but you can think of them as the final encoder output, right? Now, the encoder output contains the key. Okay, I'm a bit confused about this part. Give me one moment, I'll be back. I apologize for that. So I had a bit of confusion over here. So as you can see, the key values, so the key matrix which are encoded and the V value matrices which are encoded, they look different. They're of different color, but in fact, the decode both of these values are same. So they are the same matrices. That is the green matrix. So this both of them should be green. So the way this works is it works something like this. So if you go back to our original diagram, uh, yes, when you look at the decoder, so the decoder takes two values from the encoder. So this is our encoder, and it gives the decoder two values. So these are the key matrix and the value matrix. The decoder calculates the query matrix on its own, but it takes key and value matrix uh, from the encoder, and that is what is going on over here. So we have our encoder. Our encoder has calculated our key and value matrix, which is in fact one single matrix. Keep that in mind. And what it does, it first gives it to the first decoder layer. And then the decoder layer takes that information, uses its own query matrix, and calculates the intermediate matrix and passes it on to the second decoder layer. Now this decoder layer needs this same information again. So it uses that and then gives out the next matrix. So if we had a third decoder layer over here, this same information would have gone there and it would have taken the query matrix from here, calculated the information and given it out and so on. So let's understand what this linear and softmax layer does. It's more or less like multi-class classifier. So we have a classification of a vocabulary which contains all our words. So if you remember how we started, we had a mapping for each word. So king can be represented as 1, queen as 2, apples as 3, oranges as 4. We can reverse this as well. So if the model outputs 3, we know it's talking about apples. So we can write apples instead of 3. If the model says no, the probability is for highest for index 1, which would be the second word, queen, because 0 based indexing. So it's like, okay, we have to output queen. So that is what the software layer does. Um, it tells the highest probability in your matrix, vocabulary. So we have a vocabulary which maps each words to different numbers, and the softmax layer tells you which number is most likely to occur next in the given sentence, and that tells you the word that you need to fetch for that number. Yes, and that is basically how transformers work. One important distinction that you need to keep in mind though is a transformer is an auto-regressive model. That means it takes its own output, gives it back as an input, and uses that to calculate the next word, and so on and on and on. So, how do you tell when a sentence is ended? And for that, we have a special EOS token, which we'll talk more about in the next video. Thank you for watching. It was great having you here, and subscribe for more. Yeah, bye bye.